Let's talk about properties of determinants. The determinant of A transpose equals the determinant of A. For example, the determinant of the matrix A, 1, 2, 3, 4, 5, 6, 7, 9, 10, is 3. Find the determinant of A transpose. Well, the determinant of A transpose is just going to be 3 by the theorem we saw above. That was pretty simple. Perform the 3 elementary row operations on the matrix 1, 2, 3, 4, 5, 6, 7, 9, 10 and see what impact this has. Let's talk about properties of determinants. The determinant of A transpose equals the determinant of A. For example, the determinant of the matrix A equals 1, 2, 3, 4, 5, 6, 7, 9, 10 is 3. Find the determinant of A transpose. Well, the determinant of A transpose is just going to be 3 based on the theorem we saw above. That was pretty simple. Perform the 3 elementary row operations in the matrix A and see what impact this has on the determinant. Adding a multiple of one row to another row. Say we add 10 times row 1 to row 2. So instead of being 4, 5, 6, it's now 14, 25, 36. Let's call this new matrix B and find its determinant. The determinant of B is still 3. Adding a multiple of one row to another row does not affect the determinant. Interchanging 2 rows. Say we interchange rows 1 and 3 and get this matrix. Let's call this new matrix C and find its determinant. The determinant of C is negative 3. Interchanging 2 rows multiplies the determinant by negative 1. Multiplying a row by the constant k. Say we multiply a row 1 by 10. Let's call this new matrix D and find its determinant. So instead of having 1, 2, 3, we've got 10, 20, 30. The determinant of D is 3. Oh, the determinant's 30. Multiplying a row by 10 multiplies the determinant by 10. More generally, multiplying a row by the constant k multiplies the determinant by k. Let A be an n by n matrix. Here are some implications. If A has 2 identical rows or 2 identical columns, then its determinant is 0. Why is this? Well, using elementary row operations, if a matrix has 2 identical rows, you could kill off one of the rows and then make it a row of zeros, and then the determinant would be 0. And you could use similar logic for a matrix with 2 identical columns. If A has 2 proportional rows or 2 proportional columns, then its determinant is 0. Similar logic. Determinant of Ka is k to the n times the determinant of A. Why? Because if you multiply all n rows of a matrix by k, you're multiplying the determinant by k times k times k times k. In other words, you're multiplying it by k to the n. We can use elementary row operations to get a matrix in row echelon form, which makes it much easier to evaluate a determinant. Let A equal this matrix. Evaluate determinant of A by getting A in row echelon form. A looks like this. Okay, boy, you know what I'd want to do? I'd want to use this 2 to kill off this negative 2. That would help me to get it in row echelon form. So let's add row 2 to row 3. So here's our the determinant of the original matrix. Let's add negative 2 to negative 2, get 0. 5 to negative 5, get 0. Negative 7 to 4, get negative 3. 3 to negative 2, get 1. As we've seen before, adding a multiple of one row to another row has no impact on the value of the determinant. So these two are going to have the same determinant. And now it's much easier to work with. We'll evaluate the determinant by expanding along the first column because we have only one non-zero entry. The value of this determinant is negative 2 times the value of this determinant. Why negative 2? Because of that plus minus plus checkerboard pattern we saw earlier. This spot corresponds to a negative sign. So we have negative 2 times the determinant we get when we cross out the row and column of 2. So here's our determinant. Again, we're aiming to get this in row echelon form. Let's use this 1 to kill off this 3. So we'll add negative 3 times row 1 to row 2. Here's negative 3 times row 1. Let's add it to row 2. So negative 3 plus 3 is 0. Negative 6 plus 6 is 0. 3 plus 2 is 5. Man, if we want to get this in row echelon form, I think one thing that would help would be to interchange rows 2 and 3. Let's switch these guys up. So we end up with this. 2 times 1, 2, negative 1, 0, negative 3, 1, 0, 0, 5 times that determinant. Oh, that's actually pretty easy. This is a triangular matrix. the determinant of a triangular matrix is the product of the entries along the diagonal. Now earlier I said we wanted to get in row echelon form. Really, it's okay if these are not all ones. But it just needs to be a triangular matrix. We need to find the product of the entries along the diagonal. The value of this determinant is going to be 2 times 1 times negative 3 times 5. In other words, negative 30. That's the value of the determinant. Did it save us a lot of time? I think it was worthwhile to get it in this form. I'm not sure if it was really worthwhile to do all this stuff, but what can you say? We had to illustrate what happens when we use elementary row operations to evaluate a determinant. Here are some other determinant rules. The determinant of AB is the determinant of A times the determinant of B. Determinant of AB equals the determinant of BA. Now be warned, we've seen before that matrix multiplication is not commutative. So in general, AB is not going to equal BA, but the determinant of AB equals the determinant of BA. Why is that? Well, the determinant of AB is the determinant of A times the determinant of B, based on what we saw here above. And of course, multiplication is commutative. The determinant of A times the determinant of B is equal to the determinant of B times the determinant of A. But based on the first theorem, that's just the determinant of BA. The determinant of A inverse is 1 over the determinant of A. Why is that? Okay, the determinant of A times the determinant of A inverse by the above theorem, that's going to be the determinant of A inverse, which we know is the determinant of the identity, and that's just going to be 1. Thus, the determinant of A inverse equals 1 over the determinant of A, because this stuff multiplied together is simply 1, and so these two are going to be reciprocals of each other. A is invertible if and only if the determinant of A is not 0, and generally, the determinant of A plus B does not equal the determinant of A plus the determinant of B, so don't fall into that trap.